Today I am explaining about the use of alphanumeric codes. A binary code constructed to represent the decimal digit 26 alphabets, certain numbers of arithmetic symbols, rational operator, etc. is alphanumeric code. In other words, the codes which consist of both numbers and alphabetic character are called alphanumeric codes. Most of these codes, however, also represents symbols and various instructions necessary for conveying intelligible information. The most commonly used alphanumeric codes are ASIC, EBCDIC. ASIC stands for American Standard Code for Information Interchange. EBCDIC stands for Extended Binary Coded Decimal Interchange Code. So now we'll explain about the ASIC code. ASIC stands for American Standard Code for Information Interchange. Is a character encoding standard for electronic communication. ASIC codes represents text in computer, telecommunication equipment and other devices. ASIC code is widely used for the transmission of decimal digit, letters of the alphabets, number of special character and instruction to a telephone writer. It is a 7-bit code in which the decimal digits are represented by the BCD code processed by 0, 1, 1. ASIC binary character table, letter, ASIC code, binary. So here W, X, Y, Z are the different letters. Their ASIC code 119, 120, 121, 122. So binary form is 0, 1, 1, 1, 0, 1, 1, 1. And 120 binary ASIC code is 0, 1, 1, 1, 1, 0, 0, 0. And the next 121 ASIC code binary form is 0, 1, 1, 1, 1, 0, 0, 1. And 122 ASIC code binary form is 0, 1, 1, 1, 1, 0, 1, 0. Why ASIC code is used? ASIC code is used as a method to give all computers the same language, allowing them to share documents and files. ASIC is important because the development gave computers a common language. ASIC stands for American Standard Code for Information Interchange. And the next alphanumeric code is EBCDIC. EBCDIC stands for Binary Coded Decimal Interchange Code. Is an 8-bit binary code for numeric and alphanumeric characters. It was developed and used by IBM. It is a coding representation in which symbols, letters and numbers are represented in binary language. Epsidic differs in several respects from ASIC. The most widely used system of encoding text, dividing the 8 bits for each character into two 4-bit zones, with one zone indicating the type of character, digit, punctuation mark, lowercase letter, capital letter, and so on, and the other zone indicating the value. What is the difference between EBCDIC and ASIC? The main difference between ASIC and EBCDIC is that the ASIC uses 7 bits to represent a character, while the EBCDIC uses 8 bits to represent a character. It is easier for the computer to process numbers. On the other hand, EBCDIC is mainly used for IBM based system. It represents 256 characters. 2 power 7 is equal to 56. So these are the uses and differentiation in between alphanumeric codes like ASIC and EBCDIC. Next, importance of parity bit. A parity bit is a checking bit which is added to a block of data for error detection purposes. It is used to validate the integrity of the data. The value of parity bit is assigned either 0 or 1. That makes the number of ones in the message block either even or odd depending upon the type of parity. So why do we need parity checker? Parity checking is a basic error detection. Parity checking is the most basic form of error detection in communications. Although it detects many errors, it is not foolproof because it cannot detect a situation in which an even number of bits in the same data unit are changed due to electrical noise. Parity bit is an extra bit included with a message to make the total number of ones either even or odd. Consider the following two characters and their even and odd parity. even parity, add parity. ASIC is 1000001 and their even parity is 01000001 and their add parity 11100001. The next their ASIC form is 1010100 and even parity is 11010100 and their add parity is 01010100. In each case, we insert an extra bit in the leftmost position of the code to produce an even number of ones in the character for even parity or an add number of ones in the character for add parity. In general, one or the other parity is adopted, with even parity being more common. The parity bit is helpful in detecting errors during the transmission of information from one location to another. This is handled by generating an even parity bit in the sending end for each character. The 8-bit characters that include parity bits are transmitted to their destination. The parity of each character is then checked in receiving end. If the parity of the received character is not even, it means that at least one bit has changed value during the transmission. This method detects 1, 3 or any add combination of errors in each character that is transmitted. An even combination of errors is undetected. Additional error detection codes may be needed to take care of an even combination of errors. So different postulates in Boolean algebra. A two-state Boolean algebra comparisons of a set k is equal to 0, 1 on which two binary operations, namely logical addition called OR operation, denoted by the symbol plus, and logical multiplication called AND operation, denoted by the symbol dot, along with AND operator called NOT operator, denoted by the symbol OR, are defined and obey the different postulate in Boolean algebra. Boolean algebra may be defined with a set of elements a set of operators and a number of postulates, axioms, anything which is not proved but assumed to be true is known as a postulate. The theorems of the Boolean algebra are derived from these postulates. A set of elements is a collection of objects having a common property. If n is a set and x and y are and a and b are the two objects, then the notation is summation n denotes the x is a member of the set n and y summation not n denote that b is not a member of the set n. The most commonly postulate used to formulate various algebraic structure are as follows. Here in the given table, postulates, their primary, dual and names. First postulate, A is equal to 0 if A not equal to 1. In the dual form, A is equal to 0 if A not equal to 0. Second postulate, C is equal to A plus B. In the dual form, C is equal to A into B. That name is closure. And postulate third, A plus 0 is equal to A. In the dual form, A into 1 is equal to A. And that postulate name is identity. The next fourth one is A plus B is equal to B plus A, and its dual form is A into B is equal to B into A. That name is commutative. The fifth one is A plus of B plus C is equal to A plus B of plus C. The dual form is A into B into B into C is equal to A into B up into C, and its name is associative. And the sixth one is A into of B plus C is equal to A into B plus A into C. The dual form is A plus of B into C is equal to A plus B into A plus C. Distributive name of the postulate. And the seventh one is A plus A bar is equal to 1 and A into A bar is equal to 0, and its name is inverse. Next, binary coded decimal. Simplest binary code for decimal digits only encodes 10 digits from 0 to 9. BCD is a weighted code. The weighted codes are 8421. Same weights as a binary number. There are 6 invalid code words. They are 1010, 1011, 1100, 1101, 1110, 1111. These are the invalid codes. Example on BCD coding 13. So it's 13 is the decimal number, so its BCD form is, so simply here BCD is the group of 4 bits. So first to take 3 binary form is 0011 and 1 is 0001. So this is the binary form. Here on the table decimal and their BCDs. So for 0, BCD is 0000. For 1, 0001. For 2, 0010. For 3, 0011. 4, 0100. 6th one, 0101. 6th one, 0110. 7th one, 0111. 8th one is 1000. The 9th one is 1001. The remaining 10 to 15s are the invalid codes, means A to F. So few examples for the decimal to BCD form. So 356 is the decimal form. It is converted into BCD. So here BCD is the group of 4 digits. And 3, 5, 6. So for 6, 0, 1, 1, 0. For 5, 0, 1, 0, 1. And for 3, 0, 0, 1. So these are the BCD form. And take for 5, 6, 8. So for 8, 100, 0. And for 6, 0, 1, 1, 0. And for 5, 0, 1, 0, 1. And in the given below table, binary code, decimal numbers, and BCD code. Next to grade 2 binary conversion. Grade 2 binary. To convert from a grade 2 to binary, a similar procedure is used, but there are some differences. Carry out the following steps to convert the given gray code into binary code. Step 1. Keep MSB of the given number as it is. This is also the MSB of the binary number. Step 2. Add this MSB to the next bit of the gray code to get the second bit of the binary code. Neglect if there is carry. In the third step, the process is to be continued till the LSB is reached. So, take example and to convert from a gray to binary. So this is a 1 0 1 0. So first MSB, these are the LSB 0 and 1 is the MSB here. So take MSB as it is 1 and this 1 is add with the next MSB bit, that is 1 plus 0 1 plus 0 1 and this one is add with the another bit, that is plus 1 plus 1 0 and this 0 is added with the 0 plus 0 0. So the binary form is 1 1 0 0 given 1 0 1 0 gray code. To take another example, that is 1 1 1 0 1. So first one is take as it is, that is 1 and this one is added with the next digit 1 plus 1 0 and the next 0 is combined with the another bit, 0 plus 1 is 1 and 1 plus 0 is 0 1 sorry and 1 plus 1 is 0. So 1 0 double 1 0 is the answer here. And in the given truth table, you can do one by one. First one is take 0 0 gray code 0 0 0 0 and its gray code is 0 0 0 0 and take 0 0 0 1 and it is 0 as it is MSB bit, that is 0 and 0 plus 0 this MSB as it is take and that a digit is added with the next MSB bit, that is 0 plus 0 0 again 0 plus 0 0 0 plus 1 1. So this is the answer here. And take another, that is 0 0 1 1 third one And next this MSB is taken as is 0, and this answer is combined with the next bit, that is 0 plus 0 0, and 0 plus 1 1, and 1 plus 1 0. This 0 0 1 1, so 0 0 1 0 is the answer. And next take 0 1 double 0. So here 0 is take MSB is as is 0, and this answer is combined with the 0. Next bit, that is 0 plus 1 is 1, and 1 plus 0 is 1, and 1 plus 0 is 1. 0 1 double 0 1 double 0 0 triple 1 is the answer. We take next one. Suppose 1 0 1 1. So this MSB is taken as is, that is 0, and 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1. So seventh one is 10. Okay. This one 0 1 0 1. Okay. And next take double 1 0 1. So the MSB is take as t is 1, and 1 plus 1 0, 0 plus 0 is 0, and 0 plus 1 is 1. So double 1 0 1. Double 1 0 1. Answer is 1 0 0 1. And take 1 1 1 and 1. So this one is LSD. 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 0. So 10, and take triple 1 0. So 1 is as is 1, and 1 plus 1 0, 0 plus 1 is 1, and 1 plus 0 is 1. So this is the answer. And take 1 0 0 1. So take MSB like this, 1 1 plus 0 0, 0 plus 1 0, 0 plus 1 1, 0 plus 0 1 as it is 1 plus 0 0, 1 plus 0 1, sorry, and 1 plus 0 1, sorry, 1 plus 1 0. The next convert a gray to a binary to gray code. So here gray code, define gray code. The code which exhibits only single bit change from one code word to the next is known as the gray code. Gray code is an unweighted code, which means that there are no specific weights assigned to the bit position. It is known as cyclic code or unit distance code. Cyclic code is one in which all successive code words differ in only one bit position. This may be verified from the following truth table. So here the code word from a decimal 0 is 000, and the code word for decimal is 1 is 0001. In the binary to gray conversion, take the following steps. Step 1, keep the MSB as it is and add MSB to the next LSB, and if there is carry, neglect it and write the sum as next the bit in gray code. Continue this till LSB is reached. So in the given table, binaries are 0000 and the gray code is 0000. And the next one is 0001 and take MSB as it is, that is 0. Add the MSB to the next, that is 0 plus 0, 0, and again 0 plus 0, 0, and 0 plus 1, 1. So this is the answer. And take next binary form, that is 0 0 1 0. So it can be, take this is like this, MSB is 0 and this MSB is added to the next LSB, that is 0 plus 0, 0 plus 1, 1, 1 plus 0, 1, like this. And take one example, that is 1 0 0 1 1. So this MSB is taken as it is, that is 1. And that is 1 plus 0, 1, and 0 plus 0 0, 0 plus 1 1, 1 plus 1 0. take 11101. MSB is as it is, that is 1, and this MSB is added with the next LSB, that is 1 plus 1 0, 1 plus 1 0, 1 plus 0 1, 0 plus 1 1. So these things. You take the number 1011. So this MSB is as it is, that is 1, and 1 plus 0 is 1, and 0 plus 1 1, 1 plus 1 0. So this thing. Take another in the given in the given table, that is 1100. MS is as it is, that is 1, and the next add this MSB to the next LSB, that is 1 plus 1 0, and next 1 plus 0 0, and 1 plus 0 1, sorry, and 0 plus 0 is 0. 0 0 1 0 1 0 is the answer. We take finally 1 1 1 1. So E1 is as it is, and this MSB is added to the next LSB. So 1 plus 1 0, 1 plus 1 0, 1 plus 1 0. So this is about the gray to binary and binary to gray code conversions. Thank you.